My name is Atharva from Trinity College Dublin, and today I'll be talking about integrating zero-knowledge proofs to making them quantum safe in the XRPL ledger. This would be the flow of the presentation. We take a look at the current state of the XRPL ledger, its transaction structure, then we'll understand what are zero-knowledge proofs again. Then we'll take a look at how we integrated zero-knowledge proofs into the XRPL ledger, and a few ways in which we optimize them. Then we'll take a look at the zkSNARKs versus the zkSTARKs, which are two different zero-knowledge proving mechanisms, and then the results and future directions. Somehow the colors are a bit wrong, but that's fine. The XRPL ledger is known for its various use cases due to its key features. It is cost efficient, it performs transactions at high speed, it is highly scalable, and the main use cases involve cross-border payments, decentralized exchange, creation of payment channels, and tokenization of digital assets. Let's take a look at the current transaction structure of the XRPL ledger. So, like any public ledger or public blockchain, the sender's address, the receiver's address, and the amount being transferred is all visible on the ledger. The signature is visible as well, but though it's of no use. So this brings me to the privacy problems in XRPL and other blockchains. Take some key players in the market: XRPL, Bitcoin, Ethereum, all are fully transparent ledgers. This means any transaction performed on the ledger is got to be staying there forever. Anyone would be able to view who sent how much to who. This raises some privacy concerns in terms of the surveillance and tracking of funds, and also may lead to some financial privacy erosion. So this is where zero-knowledge proofs come in handy. Those of you who weren't there yesterday, I'll explain it to you what zero-knowledge proofs are through this example. Those who were present yesterday, today you can be the prover and I'll be the verifier. So again, let's say I have a safe which has a treasure inside it. The safe is locked by a code, and you one day come up to me and claim that you actually know the code to the safe. And naturally, since I can't verify this fact, I'm going to ask you to prove it without revealing the code. So what we'll do is, when I'm not looking, you're going to go and unlock the safe since you know the correct code, and you'll bring the treasure to me, and then I'll be able to actually verify that you actually do know the code, because the safe can only be opened by one correct code. So this is an interaction between a prover and verifier. This is what we call interactive zero-knowledge proofs. We integrated zkSNARKs, which is a non-interactive version of zero-knowledge proofs. This means the interaction between the prover and verifier can only happen once. These are the certain properties of zero-knowledge proofs. We prove a statement without revealing any information. The first property is completeness. So if the proof is true, an honest verifier will always be convinced. Second is soundness. If the proof is false or if the code is false, there's going to be no cheating provider able to convince that verifier. And lastly, zero knowledge. This means I learn nothing except the fact that you know the code. So we use zkSNARKs as the first approach in implementing zero-knowledge proofs in the XRPL ledger because they are very small in size, approximately 200 bytes. They only take 5 to 10 milliseconds to verify the proof. And again, like I said, they're non-interactive, so there's no back and forth communication required. So these are the three main steps by which we integrated zero-knowledge proofs into the XRPL ledger. We integrated a library called zkSNARK, which offers zero-knowledge zkSNARKs functionality, and it is written in C++, which is suitable for RippleD since that's in C++ as well. We then developed a circuit for the proof generation and verification. Here we try to mimic the same pattern as if it's a Zcash transaction. And we removed some unnecessary constraints to reduce the proof generation time. And then finally we integrated the circuits into the core ledger and carried out some tests. So this is the updated transaction structure now. Anyone would be only able to see the commitment, which is a hash of the sender, receiver, and the amount for that transaction. There would be a zk proof, which is never stored on chain. This verifies the transaction without revealing the details. Then we have something called nullifier, which would basically be the stamp of a transaction being successful. Think of it as a peer-to-see on the chat. Then there's naturally the fee associated with the transaction. Now let's talk about how we actually upgraded zero-knowledge proofs. So firstly, what we were using is we were using a Merkle tree to store the zk transactions. For those of you who don't know what Merkle tree is, it is a data structure to store the commitments, which I talked about in the previous slides. So what happens is, if I have to prove that I own a commitment on the tree, I have to give certain values to the verifier. One of the values is the root, which is the commitment at the topmost level. So you hash out your left and right side, and you keep on going up according to how deep you are in the tree. So with this, there is a problem that if a tree is like really deep, let's say depth 32, which is around like 4 billion transactions, it's going to take exponentially a longer time to reach that point. Hence, it's going to take longer time to verify, hence longer transaction time. So we switched to a incremental Merkle tree. What this does is it pre-computes the nodes which are not really involved in proving this specific path. So in this way, the transaction time increases, but it's not that much. Then the second improvement which we have worked currently is we used Poseidon hashes to store the commitments instead of the XRPL's native SHA-512 again, this sped up the transaction time by a lot. And then finally, we upgraded to zkSTARKs, which is scalable, transparent arguments of knowledge, also known as post-quantum zero-knowledge proofs. So let's take a look at the results. So this is a graph of transaction time by the tree depth and the approach. So the small blue subbar you see is a normal transaction carried out on XRP. Typically takes about 3 to 5 seconds. Then you have this orange subbar plot, which is a normal SNARK transaction. So here, as you can see, as we go deeper and deeper into the tree, so 2 raised to 32, around 4 billion transactions. Since it has to reconstruct the tree again to verify the proof, the proving time is actually more than the proof generation time you see. Then on the green bar consists of the optimized version of zkSNARKs. So from here you can really tell that since we use the incremental Merkle tree, even at the depth of 2 raised to 32, the proving time is kind of similar as proof generation time, and the transaction still doesn't take more than a minute to do. And then finally we have zkSTARK transaction, which is still a work in progress, so we don't really have all the readings as we have for the other 3 approaches. So from here you can see that since it's post-quantum and the proof size is a lot larger than the traditional zkSNARK, it takes around 2 minutes to just generate the proof alone. Once you go deeper and deeper into the node, then it's still going to take even more time to verify. So with that said, I would like to end my presentation. Again, like I said, this is a work in progress, so we're still working on it and trying to get more results as we progress.